So I want to show you two ways to solve this problem. This is the AP class Web of Science number 13 and the circuits review. This is from Survey Physics for Scientists and Engineers, Volume 9, Chapter 28, Problem 19, WI. And essentially we have a circuit here with a battery and 4 resistors, and we want to figure out what the power is through each of these resistors, consumed by each resistor. And one way to do that is to figure out what the current is through each resistor. And so that's what we're going to do. And then I'll leave it up to you to solve for the power, but I want to just concentrate here on how does one find the current going through each resistor. For my problem, R1 here is 3 ohms, R2 is 2 ohms, and the voltage in the battery is 21 volts as shown here. So I've got that redrawn here exactly as what was shown in the book. And I've gone ahead and in the traditional way, what we'll do is we will reduce this down to an equivalent resistance, 1 resistor, and we will then backtrack to figure out what the voltages and what the currents are. So we start with our 4 resistors here. These two are in parallel, and so this is the equation to get the resistor in parallel. 1 over 2 plus 1 over 1 is equal to 1 over our resistance in parallel, and when that happens, when you do the calculation, you see it's 2/3 of an ohm. So this can be reduced, this little guy here is reduced to this guy here. Okay, and now we have three resistors in series, and resistors in series simply add the up. So we have the 3 plus the 0.667 plus the 4, and that gives us 7.667. And so all 3 of these here around the dotted line are here around this dotted line. Okay, and hopefully you're familiar with that and you're able to reduce it down. The hard part, I think, is then taking these diagrams, going back up and solving for the currents. Okay, and so to return up the hill, right, we're going to look at what we do not know, and what we don't know here is we don't know the current through this resistor. We know the voltage drop across this resistor is 21 volts. The voltage drop across this battery is 21 volts for sure. And then if we just move out, we see that that's also 21 volts, 21 volts, 21 volts, 21 volts. So the voltage drop across my resistor is also 21 volts. We know from Ohm's law, or the simplified Ohm's law version. Okay, and the voltage drop across the battery is 21 volts, and the voltage drop across the resistor is 21 volts. That's what Ohm's law is telling us. And the resistance is 7.667 volts, and we can calculate a current of 2.74 amps. Okay, now what do we do with that? Well, this is the thing we don't know. So when we go back to here, the thing we don't know through this resistor, right, is the current. And that current we know is 2.74 volts. Sorry, 2.74 amps. Silly me. 2.74 amps. And because this is one continuous non-branching path, we know the current through this is also 2.74 amps. And the current through this is 2.74 amps. Okay, and so the current all the way across throughout the battery and throughout the circuit is 2.74 amps. So what do we not know about this guy? And why do we care about the orange circle? We care about the orange circle because we want to figure out what is going on up here. Well, we know the current through the resistor, and we know the resistance. So what we do not know is we do not know the voltage drop across the parallel resistor. I'm going to call that delta VP. That's equal to the resistance, in this case the parallel resistor, times the current, and we see that this is 0.667 ohms, and the current is 2.74 amps. And when we do the calculation, we get 1.827, and this is volts. Okay, so what do we do with that? Well, we take that thing we just calculated and we are going to apply it to this. So the voltage drop across each of these resistors is 1.827 volts. We know the voltage drop has got to be the same. We know the voltage drop across this from here to here is 1.827. And those dots are redrawn here and here. Therefore, the voltage drop there is 1.827. And the voltage drop here is also 1.827 because the left and the right sides of this, the top and the bottom sides of that 1 ohm resistor, touch that. And so we know that this is 1.827 volts. So what do we not know about this? Well, of course, we don't know what the current is through each one. And so if we do a little calculation, I2, you see that that's delta V over R2. And the voltage drop across that is 1.827 volts divided by 2 ohms. And we see that that's going to be 0.913 amps. Okay, so going through this resistor is a current of 0.913 amps. And then we can do the same calculation here. I1, the current going through the 1 ohm resistor, is delta V1 over R1. Delta V1 is the same as delta V2. R1 is 1 ohm, and therefore the current here is 1.827 volts. So this current is 1.827, gosh, I said it again, amps, gee whiz, sorry, 1.827 amps. And we know that this current is 2.74 amps, and we know that this current is 2.74 amps. Okay, and now we have everything we need to know to solve for the power. Remember, power is IV, that's one equation, and it's also I squared R, and it's also delta V squared over R. Okay, and so this is the traditional way of solving this problem, where you take the resistors in series and parallel, you break it down, and then you build it back up again, knowing, playing little forensic detective on the way back up. You can do this method because there's one battery, and we can do that with the traditional way. There's another way to do this, and that is using Kirchhoff's laws. And I want to show you how to solve this exact problem using that method as well, and we will get exactly the same results here, the same currents through each resistor. You can decide which method suits you best for this kind of problem. If you have multiple batteries, for example, then you have to use Kirchhoff's. Or if you have capacitors, then you need to use Kirchhoff. Or if you have an inductor, then you need to use Kirchhoff. So Kirchhoff works everywhere, and I'm going to show that in the next video.